On January 20th, 2026, your GPS quietly started lying to you and almost nobody noticed why. Airlines were secretly rerouting flights, satellites were being put into emergency mode, and astronauts on the ISS were told to move to a different room. No earthquake, no volcano, no terror attack, just our own sun, doing something it hadn't done in over 20 years. And here's the part that should genuinely unsettle you next time we might not be so lucky. This is the story of the most powerful solar radiation storm since 2003 and what it quietly revealed about how fragile everything we depend on actually is. To understand why this was such a big deal, you need to know something that most people never think about: the sun has a temper, and it runs on a schedule. Every 11 years, the sun cycles through what scientists call a solar maximum, its most explosive, unpredictable phase. Solar Cycle 25 hit its peak around late 2024 and early 2025, and it turned out significantly more intense than anyone had forecast going in. NASA confirmed that Cycle 25 ran hotter and wilder than their own models predicted, and that admission from the world's top space agency should give you pause. Because if the experts can't accurately predict when our star is going to explode, that's a problem, and I'll get back to exactly why in a few minutes. But first, let's get clear on what actually happened, because there are a few different types of solar events, and mixing them up is how misinformation spreads. When the sun erupts, it launches three things simultaneously: X-rays and ultraviolet radiation, high-energy charged particles called protons, and massive plasma clouds called CMEs. The X-rays and UV travel at the speed of light and hit Earth in 8 minutes. You can't do anything about that. It's already done. The high-energy protons arrive 30 minutes to a few hours later, and it's these particles that cause solar radiation storms, rated on a scale from S1 to S5. And the plasma cloud, the CME, drifts in over 1 to 5 days and triggers what's called a geomagnetic storm, which is a whole separate kind of chaos. On January 20th, Earth got all three at once, and the radiation storm alone hit S4, the second highest category on NOAA's scale. NOAA's Space Weather Prediction Center posted on X an S4 solar radiation storm is in progress, the largest in over 20 years. S4 is classified as severe. It's rare enough that most space weather scientists can count the number of times they've seen one on one hand. The last S4 was in October 2003, the Halloween storms, which triggered a blackout in Sweden and destroyed power transformers in South Africa. So, when the S4 alert dropped on January 20th, 2026, the global response was immediate, and the behind-the-scenes scramble was far bigger than most people realized. Here's the timeline, and this is where it starts to feel genuinely unsettling. So stay with me. It started on January 19th with a sunspot region, a magnetically complex, unstable patch on the sun's surface that had been silently charging up for days. Without warning, it detonated, unleashing a torrent of X-rays and energetic protons that immediately began racing toward Earth. The X-ray burst hit in 8 minutes flat, instantly disrupting high-frequency radio communications across the entire sunlit side of the planet. Pilots on transoceanic routes suddenly lost their primary radio links, a reality check that these systems have no redundancy against the speed of light. Then the proton stream arrived, and over the following hours, SWPC's sensors escalated the alert all the way to S4 as the proton flux just kept climbing. Simultaneously, the CME that had been launched in the same eruption was barreling toward Earth at millions of kilometers per hour. It hit at around 2:40 a.m. Hanoi time on the 20th, slamming into Earth's magnetic field and triggering a G4 geomagnetic storm, severe, second highest on that scale too. So, within a single day, Earth was simultaneously absorbing an S4 radiation storm and a G4 geomagnetic storm, what scientists call a compound solar storm event. SWPC forecaster Sean Dahl later said, "We made a lot of phone calls to make sure every critical infrastructure operator knew what was going on." NASA, the FAA, FEMA, and power grid operators across North America were all contacted and began running their emergency protocols within hours. Up on the International Space Station, the crew was told to move to the most shielded modules, the same precaution they'd taken during the big geomagnetic storm in May 2024. And here's something that should stop you in your tracks. Those astronauts weren't just being cautious. They were protecting themselves from radiation that would have genuinely harmed them. An unprotected astronaut during an S4 event would absorb a radiation dose equivalent to multiple chest X-rays in a matter of hours, not fatal, but not nothing either. Now, while all of this was happening up in space and in government emergency centers, something completely different was unfolding down on Earth's surface, and it was beautiful. The charged particles from the CME lit up Earth's magnetic field lines like a neon sign, and the aurora borealis went absolutely haywire. The northern lights were spotted as far south as Alabama and northern California, places that might see them once a decade under normal circumstances. In the UK, Australia, and Canada, social media blew up overnight with photos of green and purple skies that looked, frankly, like something from another planet. And here's a tip worth bookmarking, even if the lights aren't visible to the naked eye. Your phone camera is more sensitive to those wavelengths than your eyes are. Solar physicist Ryan French from Colorado Boulder explained that auroras come in 20-minute bursts called substorms, so when you hear there's activity, move fast. The lights were breathtaking, but here's the thing about this story that I want you to really sit with for a second. The exact same particles that created those beautiful auroras were simultaneously trying to fry satellites, disorient pilots, and overload national power grids. It's the same energy, the same eruption, the same storm, just different surfaces receiving it, and depending on where you were, it was either magic or a crisis. Right. So let's get into the damage, because this is the part that most science videos gloss over. And honestly, it's the part that matters most. An S4 radiation storm does its worst damage to satellites in polar orbits. High-energy protons punch straight through standard shielding and scramble onboard electronics. Satellite operators worldwide went into emergency mode, actively powering down non-essential systems and rotating their birds away from the most exposed angles. GPS took a hit too during the associated geomagnetic disturbance. Positional errors climbed anywhere from 10 to 50 meters, which sounds minor until you're landing a plane in low visibility. During a comparable geomagnetic storm in May 2024, John Deere reported that farmers using GPS-guided precision tractors were getting errors that made the systems unusable. Think about that: a star 150 million kilometers away caused a tractor in Iowa to veer off course because of a ripple in Earth's magnetic field. Aviation got hit harder. Polar flight routes depend on high-frequency radio, and those frequencies get completely blanked out during S4-level radiation storms. Multiple airlines were quietly rerouting their transpolar flights during the peak of the event on January 20th, adding hours and thousands in fuel costs per aircraft. And for power grids, this is where it gets really scary. The G4 geomagnetic storm was inducing enormous electrical currents in transmission lines across the continent. Think of it as the sun remotely injecting electricity into wiring that was never designed to handle it, and the first thing that gives way is the transformer. In the Halloween storms of 2003, South Africa lost multiple high-voltage transformers, the kind that take 6 to 18 months to manufacture and replace. A country without its major transformers is a country that goes dark for months, not hours, not days, months, with all the cascading failures that implies. Fortunately, in January 2026, grid operators moved fast enough to protect the most vulnerable transformers, but here's the thing: nobody's saying out loud. We only had 15 to 60 minutes of advance warning from NOAA's satellites at the L1 Lagrange point, barely enough time to act, and only because everything went right. That warning window is the same width it was in 2003, 23 years of technological progress, and we're still working with less than an hour's notice. I'll come back to that, because it's probably the most important unresolved problem in this entire story, but first, let's talk about whether any of this actually affects you personally. The short answer is on the surface. Earth's atmosphere and magnetic field do a solid job of keeping the worst of the radiation off your skin. But research in environmental health perspectives found that on high solar activity days, patients with existing heart and lung conditions showed measurably reduced function. A Brazilian study linked strong geomagnetic storm days to a statistically higher incidence of heart attacks, particularly among women. Correlation, not proven cause, but worth knowing. Harvard researchers have also found links between elevated solar activity and disrupted sleep, likely because the geomagnetic fluctuations interfere with melatonin production. And if you or someone you know has a pacemaker or an electronic medical implant, the official guidance during an S4 event is clear: stay indoors, stay calm, don't exert yourself. None of this is panic-inducing at S4 level, but it's a sharp reminder that the sun is not some distant, irrelevant object that scientists study through telescopes. Now let's pull back and look at the bigger picture, because January 2026 was not a freak accident. And what comes next is genuinely concerning. The year 2025 was, by almost every metric, the most intense year for solar activity in living memory. In June 2025 alone, a single sunspot region produced over 160 major eruptions, and scientists later confirmed that solar cycle 25 peaked harder and earlier than any forecast model had suggested. That systematic failure of prediction matters, because our entire infrastructure protection strategy is built on the assumption that we can see this stuff coming. And here's the uncomfortable truth that was hiding behind all the aurora photos and the press releases about how well the January response went. January 2026 was an S4 severe rare, genuinely worrying, but it was not the one we actually have to fear. The one we fear is called a Carrington-level event, and compared to January 2026, the Carrington event makes the S4 look like a spark from a campfire. In September 1859, astronomer Richard Carrington watched through his telescope as the sun released the most powerful solar flare ever recorded in human history. That flare was estimated at around X45 in intensity, roughly 5 times more energetic than the biggest flare recorded in October 2024, which clocked in at X9. In 1859, the only electronic infrastructure humans had was the telegraph, and the storm was still powerful enough to set telegraph offices on fire and electrocute operators. Auroras were seen as far south as Cuba and Hawaii, so bright that gold miners in the Rocky Mountains woke up thinking it was dawn at 1 a.m. If that same storm hit today, a 2013 analysis by Lloyd's of London estimated the economic damage could easily exceed $1 trillion US. We're talking about continental-scale blackouts lasting months, the collapse of GPS-dependent logistics, and communication systems going dark across entire hemispheres. And the brutal scientific reality is this: a Carrington-level event is not a question of if, it is unambiguously a question of when. January 2026 was the sun clearing its throat a serious event. Yes, but still several orders of magnitude below what the historical record tells us is possible. So, what are we actually doing about it? And is the answer enough? Because that question has a genuinely uncomfortable answer. On the positive side, January 2026 demonstrated that our early warning systems work. SWPC got the alerts out fast, and the response was impressively coordinated. NOAA's DS-Cover satellite at the L1 Lagrange point gives us that 15 to 60 minute window before a CME hits, and in January, that was enough to make a difference. ESA's Solar Orbiter, launched in 2020, and NASA's Parker Solar Probe, which has flown closer to the sun than any spacecraft in history, are feeding us unprecedented data. That data is helping scientists build models that can predict space weather better, though better still means a few hours, not days, which is a sobering reality. The Holy Grail reliable 24 to 48 hour advance warnings is still roughly a decade away, according to the researchers working on it. And that gap is dangerous. On the protection side, power companies have started deploying GIC blockers, geomagnetically induced current blocking devices, on transformers in high-risk areas. Think of them as circuit breakers specifically designed to stop the sun from injecting electricity into the national grid, and they work, but they're not everywhere yet. Satellite operators have gotten much better at putting their systems into safe mode during storms. And aviation authorities now have polar rerouting protocols that activate automatically. The UK, the US, Australia, and Canada all have national space weather action plans, which sounds bureaucratic, but genuinely means there are people whose entire job is this problem. But here's where we come back to that warning window problem I flagged earlier, because this is the thing that should actually keep you up at night. For a Carrington-level event, 15 to 60 minutes of warning is not enough to protect the power grid, because shutting down a national grid safely takes longer than that. You can't just flip a switch and turn off a country's electricity. Transformers have to be de-energized in sequence. And if you miss that window, they burn. And burnt transformers at that scale aren't replaced in days or weeks. They're custom built, shipped internationally. And the queue to get one is already months long. February 2026 underscored all of this when a sunspot region spaceweather.com called a flare factory unleashed an X8.3 flare just weeks after January's S4. That February event triggered another G4 geomagnetic storm, stunning aurora displays across Europe, and another round of infrastructure operators scrambling to protect their systems. The sun is not done. Solar Cycle 25 won't fully wind down until around 2030, and some of the most extreme events in a cycle can occur during its declining phase. So, what does all of this mean for you, not as a space enthusiast, but as someone who uses GPS, flies on planes, relies on electricity, and has money in a bank? It means the sun is the single most powerful variable in the stability of modern civilization, and most people go their entire lives without ever thinking about it. It means that the beautiful aurora your friend posted last January was created by the same energy that could, under the wrong conditions, darken entire continents. And it means that the gap between a close call and a genuine civilization-level disruption is thinner than most governments are comfortable admitting publicly. January 2026 was a close call, serious, well handled, and a genuine testament to how far space weather forecasting has come since 2003. But we also got lucky the CMEs magnetic field was not in the worst-case southward BZ orientation that would have coupled most destructively with Earth's magnetosphere. Had it been, the story you'd be hearing wouldn't be about disrupted GPS signals and rerouted flights. It would be about something far more serious. Here's the final thought I want to leave you with, and it's one I genuinely find myself coming back to. Every culture in human history without exception has treated the sun with reverence, awe, and a healthy measure of fear. For most of history, we thought that was superstition, but the more we learn about what the sun is actually capable of, the more those ancient instincts look like wisdom. We built a civilization that runs on electricity and satellites and GPS, and then we pointed all of it directly at a nuclear furnace with a 23-year tantrum cycle. The January 2026 S4 event didn't break anything permanently, but it reminded every scientist, every grid operator, and every government with a space weather desk of something important. The next big one is coming. We don't know when. We don't know exactly how big. And our warning window is still measured in minutes, not days. The question is whether we'll have done enough by then, and honestly, based on what January 2026 revealed about our current gaps. The jury is very much still out. If this got under your skin even a little bit, good, that's the right response to a genuine, underappreciated risk that affects every single person on this planet. But here's what I want you to chew on after you close this video. January 2026 was the sun at S4 2 steps below its maximum theoretical output. So, what happens when it goes all the way? What does an S5 actually look like, and does humanity have any real plan for it? That's the next chapter, and it's one of the most important conversations we're not having loudly enough as a society. Stick around, because that video is coming, and I promise you, once you've seen what scientists think a maximum level solar event could actually do, you won't look at a sunny day the same way again.